So the first one is aleovalent doping. What's aleovalent doping? Aleovalent means that what you're putting on what you're substituting for has a different charge. The valency is different. So, for example, if we did, let's say we're doing NaCl, right? That's our host lattice is NaCl. If we did an aleovalent substitution, that would be something other than a +1 on the sodium site or a -1 on the chlorine site. So we could say oxygen, right? If oxygen were doped into rock salts, I don't even know if that's possible, but if you did, oxygen is 2-, and you're putting a 2- on a 1- site. What problem will this create, and how do we fix it?
It's not balanced.
The charge neutrality is not balanced, and that has to be balanced. So how do we fix it? If you put, the nomenclature for this, by the way, is O on a chlorine site is excess negative, so they put a little dash. You don't need to do that for the test. That's just the way this is done in the field. Yeah, that it's relative to chlorine, it's an extra negative charge. So how do you fix this? You have two options. If it's overly negative, we can either add positive, that means an interstitial. So we could add a positive charge, or we could remove negative. Yeah, that's an oxygen sitting on a chlorine site. So the chlorine in the subscript means that the oxygen is on the chlorine site. And then the little apostrophe up top means that in doing so, you're now overly negative from what it ought to be by one charge. Right? It ought to be a -1 there. You put a -2. So it's overly negative by one charge. You don't have to know that nomenclature. If you take a ceramics class, you'll learn it, but you don't need it for this class. The concept's important. It's too negative. Therefore, we must either add positive or remove some negatives. Which one's it going to do? It's going to remove negative. I mean, technically, it's going to do both, but what are the ratio of those defects? There's going to be so many more of the removing negatives than the adding positives, because adding positives is stuffing something in the lattice, and that's generally a hard thing to do. Lattices are generally close packed. You don't have lots of just empty space. So how can we remove a negative? What do we do? What can we remove? Well, what's negative in the formula? You got sodium and chlorine. We're going to remove chlorine. How much chlorine are we going to remove for every dopant? This is going to be a 1-to-1. So the formula gets written like this. NaCl. Now we're going to write 1 - X. The 1 - X is the substitution, right? So oxygen right here would be X. So for every oxygen you put on there, that's for every X amount of oxygen that you put on there, you take away 1 chlorine just because you substituted it, right? You pulled out the chlorine to put the oxygen there. Now, the other thing we have to account for is the additional removal of chlorine that has to happen because of charge neutrality. So it's not just going to be 1 - X. What's it going to be? 1 - 2X. For every X, there's 1 that's removed due to substitution and 1 that's removed due to charge neutrality. Make sense? So this is a non-stoichiometric formula that comes about because of this aleovalent substitution. Yeah?
So the 2x is because it's O2?
The 2x, 1x, if it was 1 - X, that's because the oxygen is on the chlorine site. That accounts for the first 1 - X. Why is it 1 - 2x? The second chlorine that has to be removed is because for every, let me write this down. For every oxygen on a chlorine site, we need an additional chlorine vacancy. And again, that's for charge neutrality reasons. So you get, the first X is gone because you put an oxygen on there. The second X is gone because you had to for a vacancy. Should we do another example? We can do a bunch of these. Yeah, Landon?
So I was just clarifying that, like, so doping means that you're just taking it and you're substituting, you're hitting it.
We're talking about a substitution. Yeah.
Knocks one of them out and it's replaced, but then in order to
Yep.
neutrality, one just leaves.
An additional one has to be missing in this case. Yeah.
If it's a higher negative.
Yeah, we can come up with all sorts of defects. We'll do a few different examples. Yeah.
Could you do an example where it's like Cl2 or something like that? Like, how would that change?
Okay, yeah, let's do another one. So let's do MgCl2. So MgCl2, magnesium chloride, we can put an aleovalent substitution on either site, the cation or the anion, right? So let's put, I don't know, just making stuff up, let's put an aluminum 3+, on the magnesium 2 plus site. What will that do? Well, an aluminum 3 plus on a magnesium 2 plus is overly positive. So we write it like that. Aluminum on a magnesium gets the dot. That means that it's one extra positive charge, okay? Again, this nomenclature doesn't matter. It's important that you realize what we have excess of. In this case, we have excess positive, right? So if we have excess positive, we can either remove positive or we can add negative, okay? Again, adding is almost never the right answer because it's harder, it costs more. So let's think about removing positive here. What would we have to remove in this case? So we're going to remove the positive. That's going to be the magnesium. So let's write out our formula. It was magnesium 1 minus X, aluminum X. Therefore, for every aluminum that we put in on a magnesium site, this 1 minus X and X just accounts for the substitution. The next thing that we do is we account for the additional things that have to be taken out. So for every 1 aluminum that we put there, we get a +1 excess charge. But if we take away a magnesium, how much positive charge are we taking away? We're taking away 2. So you can't be like a 1-to-1. This can't be 1 minus 2x like before, because then we go the other way. We end up with not enough positive. You take a half an x away. Basically, for every 2 of these, you take away 1 of those. So this becomes x over 2. Wait, sorry, no, that's wrong. I said that wrong. It would be 1 minus x. You can write out like this if you want to make it clear. Minus x over 2, right? So the first one is from the substitution, and then the other one is for every 2 of those, you get one of these missing, okay? So you could combine those, and it's 3/2 x, not 1/2 x. 3x over 2, aluminum x Cl2. Now, to your point, the question over there, we'll do it now where it affects the chlorine, just because that's the one with the 2. But everybody clear on this? Does that make sense? If it doesn't make sense, it's okay. Raise your hand. What's up?
Could you make that all whole numbers?
You could, but they don't. You don't do that. Yeah. Yeah, Carlos?
Say the steps one more time. So first
Okay. First thing you do is you think, okay, which site is it going to go on? If it's a positive ion like aluminum, assume it's going to go on the cation site, right? Then you compare the charge of those two things. Aluminum is 3 plus. This thing was 2 plus. So aluminum sitting on that site is overly positive. It's excess positive. If it's excess positive, you say we have to either remove the positive or we have to add negative. Removing is the usual defect. Vacancies are much more prominent than interstitials. So now that we know that we have to remove positive, you look at your formula and you say, all right, what's positive here? Just the magnesium. So then you start writing your formula. First you write the substitution, 1 minus x and x. And then the second thing is you account for neutrality. You say, okay, it's not just 1 minus x because we have to have some vacancies here. How many vacancies? You say, well, since every one of these defects gives me an excess charge of 1, but if I take away a magnesium, that takes away 2 at a time, then it's going to be an additional x over 2 that we take out. Ryan?
So is it safe to say that the fraction of x will be like the ratio of charge from like aluminum to magnesium?
I haven't thought of a general rule for this. I always do it just case by case in my head. Let's do a few more examples and see. Okay, let's do another one. Okay? So this time let's do that same compound, but let's dope on the chlorine side. Okay? So let's put a 2 minus. Let's put oxygen on this one. What's going to happen, right? No, let's put a, oh, that's not going to work. Let's pick a different compound. Let's do Al2O3. Okay, Al2O3 is our host. And let's put a, let's see, which one do we want to do? Let's do something goofy. Let's do like a niobium 5+, right? So Nb2O5 is the oxide. In that oxide, this guy's 5+. So we're going to put a 5+ on this 3+ site. Let's see what it does. Yeah, Ryan?
For a question that's like this, would you say Nb2O5 is, you're putting that whole thing into?
I would probably just tell you that Nb5+ is being doped into it. And the understanding is that, well, where do you get Nb5+? You get it from Nb2O5. Yeah. So that's what we're going to dope in there. So this means, using our little notation, that we've got Nb sitting on an aluminum site. That's an Nb5+, on a 3 plus site, so it's overly positive by 2, right? It's got 2 excess positive charges, okay? Therefore, if it's got positive charge, we need to get rid of positive charge. If it's overly positive, we need to remove positive, or we need to add negative. In this case, since it's 2 positive that we are excess 2 positive, adding a single oxygen would do it, right? If we could add something, it's just that that's not really feasible, right? Because oxygens come in 2 minuses at a time. So for every 1 substitution, for every Al2, for example, if we did add it, we could say Al 2 minus X, niobium, X, oxygen 3 plus X. That would be one where it's all the same. This comes from the substitution. Doesn't matter how many you started with, 2, 3, 5 over here. For every 1 that you replace, you get 1 niobium there. So this is just substitution. And then because you have to make up for that it's overly positive, if you're going to add negative, then it would be 3 plus X. Now this isn't likely to happen because stuffing oxygen, which is massive, into the structure, it's just not going to happen. So the key here is this wouldn't be a good answer because this is unlikely. It's technically correct. That is a correct non-stoichiometric formula. It's just not very likely. It's not a common defect. There's a much more common one, which is to remove positive. So what's going to happen if we remove positive? We are excess 2 positive charges, right? We've got 2 extra positive charges. What do aluminums come in? They come in 3s. So this is complicated, right? If you take away 1 aluminum, now you are deficient by 1. So the ratio has to be a 2 to 3? Is that what the ratio has to be? For every, let's see, for every 3 of these, we would be 6 positive. We could remove 2 aluminums. So it's a 3 to 2 ratio, okay? So I think the easiest way to do these is just to write it out in steps. I would say, okay, first off, aluminum, 2 minus X, niobium, X. That's just for the substitution, okay? Then oxygen 3. Then you say, okay, for every 3 substitutions, you remove 2, right? For every 3 substitutions, you remove 2. So it's going to be minus 2/3 X. 2X thirds. Is that right?
Yeah.
I think it is. I think that's right.
Yeah, because 3 plus 2/3 of 3 is 5.
You need to remove 2, so Al is 3 plus.
You could always double check it, by the way. Punch in numbers. Pick a value for X. Like, let's say that you're not sure about this and you want to double check it. Assume that, okay, X equals 0.1. When you punch in X here, you better end up with positive 6 out of these things, right? So let's try it. If I punch in X equals 0.1, do I get a positive 6 to offset my negative 6 from my oxygens? I better. So let's try it. We'd say if that's equals 0.1, then aluminum, remember, which is 3 plus, there is 2 minus 0.1 minus 0.2 over 3. Somebody tell me what that is. Meanwhile, you've got niobium, which is 5 plus, and that's just going to be, take that whole thing on that one above and multiply it by 3. Meanwhile, this one is going to be 0.1 times 5. Add those up. Am I missing something? Oh, because these have 3 charges. It's a plus 3, and this is 5 plus. So that's why the 3 and the 5 are there. What did you guys get for that?
You had to pick a decimal.
I had to pick a decimal. Oh, yeah, you're right. That would have been easier. Anyways. Because in reality, most things don't have high solubility. They only dissolve. 10% is already like a ton to dissolve in things. Most things aren't very soluble. Like 1% sometimes you can't even get. So 2 times... Wait a minute. 2, that should be minus. Sorry, not times. Okay, 2 minus 0.1 minus 0.2 over 3. Take that whole thing, times it by 3. And then add from that 5 times 0.1. And it adds up to 6. So we did it right. Okay? Are there questions about this? Does this make sense? Should we do another example? One more? You guys tell me what you want. What compound do you want to see?
Let's go on the vacancy concentration.
Let's do one more quick one. Somebody tell me what they want. We'll do it fast. What doped into what? Can you what now? Yeah, and you can dope on multiple different sites. Yeah, let's say you had a material like you've got lanthanum to strontium Al2O7. That compound exists. You can dope on all of these sites. All 4 of those different sites you could introduce dopants. You can actually introduce co-dopants, right? We're not going to get into that in this class. I'm not going to test you on it. But on the lanthanum site, you could dope on that site aluminum and gadolinium, right? 10% of each. So you can get really complicated things. Yep, that exists. So, anybody want to see something in particular? Or do we? H2O with nitrogen. All right. Nitrogen going into H2O. So we're going to put the nitrogen on the oxygen site. What's the flavor of nitrogen? It can take multiple different oxidation states.
Say it's
3 plus or 3 minus? I think you can do both.
minus 3.
Minus 3, okay. So if you're putting a nitrogen, and that's a 3 minus, on an oxygen, and that's a 2 minus site, then we're overall 1 negative, right? We have an excess negative charge, so we can either remove negative, or we can add positive. This isn't a scenario where adding positive, and I assume we're talking about like ice, so it's like a solid, so you actually have interstitials. Adding a solid would make sense here because ice is a polar molecule. It's if you look at the crystal structure of it, it actually has a lot of empty space because it's a polar molecule. Like it forms these channels, like it bonds essentially negative to positives all the way through it. And so you get lots of big open spaces. So the point is, if we needed to add an extra positive charge, the thing that we're adding that's positive is hydrogen, which is tiny, and it's a really open structure. So this might be a scenario where the interstitial is fairly likely. It might have a low energy cost associated with it. So in that case, one possible scenario for this would be H2 plus X, oxygen 1 minus X, nitrogen X. That would be actually a maybe semi-feasible scenario. Okay? All right, let's keep going. If you got more questions, let me know.
Could you also just take out an extra oxygen?
Or you could remove oxygen, yeah. And again, the ratio here, since you're excess negative by 1 and you pull out an oxygen and that takes away 2, it's going to be the same thing we saw before. It's going to be H2O minus 3 halves X. All right, next one says vacancy concentration given an activation energy and temperature. You've seen this before. Nothing tricky here. This will be straight out of like the book problem homework where you have the number of vacancies. I'm going to use lowercase NV equals the total number of sites multiplied by the exponential of our activation energy for vacancies over KBT. The reason we use KB as opposed to R is because KB you do if you're doing something on like a per atom basis. If you use R, it's on a per mole basis. We usually don't have a mole of vacancies, right? An Avogadro's number of vacancies would be a ton of vacancies. It's much more common to talk about onesies, twosies, a few dozen. So we're going to use KB instead of R because it's done on a per atom instead of a per mole basis. So this is the difference here, and not this I think where a common mistake is that this is the number of vacancies. Big N is the number of sites on which you could have that vacancy. And if you want the concentration of vacancies, or the fraction, really, this is the fraction, NV over N. This is the fraction, or the percent, right, of vacancies. If you multiply that by 100%, you could get the percent. As opposed to the raw number. Yeah?
So N is big N is just total number of
Sites where you could have that vacancy. So, for example, let's assume this scenario. Let's assume that you had and I don't remember if this is on the test, honestly, so I don't know how much you should pay attention to this, but what I'm saying is correct. I just don't know if it's on the test or not. Let's assume that you've got rock salt, and so you've got your atoms on the corners. By the way, you all need to take some cube drawing classes. There are some remarkably bad cubes rolling in on the homeworks and tests. I mean, I'm not amazing, but y'all are bad. Really bad. Okay, so get your atoms on the faces, right? Now, this is FCC. If we did a rock salt structure, we have to account for the other lattice, right? So that gives us, the other sublattice is that you've got, let's say, anions located on the edge centers. So I'll draw my anions as X's, okay? So in this compound, you have two different sublattices. Sublattices for the cations, sublattices for the anions, right? They are both FCC. Just one's shifted by half of a unit cell over. So, Ryan, to your question, NV versus N. N would be if you could add up all the number of, say, red sites, right? So let's say we had like 4 grams of material, right? 4 grams of rock salt, NaCl, right? You could use the density of rock salt and figure out, let's see, how would you do this? We know that the density is equal to the mass over volume, right? For us, that's equal to Z, the number of formula units, times the molecular weight of the formula, over A cubed times Avogadro's number, right? So from the density, if I gave you the mass of it and the density, you could figure out how many molecular weight there are. Let's see. How would you solve this? I'm messing this up. If I gave you the mass and the ultimate, what you need to figure out is how many of these red sites are we talking about? In 4 grams total, how many of these are we talking about? Okay, so how about this? Just do, in 4 grams total, okay, use the molecular weight, go from mass to moles, right? So you go from mass to moles, right? And then you go from moles to number of atoms. You do that using molecular weight. You do that using Avogadro's number. The point is, once you've got the total number of atoms in this compound, you know the number of sites, right? The number of sodiums is the number of sodium sites there. Okay? Yeah, question?
Could you just do the mass that you're given divided by the mass of the unit cell, and get how many unit cells, and multiply that by the number of atoms in the unit cell?
Yeah, that would work too. That would work. The point is, this would give you the N that you're looking for. So then if I said, okay, that's for a perfect material, a defect-free material, now tell me the fraction of these red sites that are actually empty due to vacancies forming, right? And to do that, you would go NV, or the total, if I asked for the total number of vacancies, in that mass of material, NV, well, you'd say, okay, NV, I know what N is, so you do exponential of the negative activation energy for vacancies divided by KBT. Okay? KB is a constant, 8.617. You guys saw Stranger Things, come on. Nobody? Do you need to call Susie in the middle of the exam? No?
That's Planck's constant. Come on.
No, isn't it Boltzmann on the show?
On the show was Planck's constant.
Planck's constant.
Oh, my bad.
God, fake fan.
Fake fan, done. Turning in my card. You're right, it was Planck's. So it's Boltzmann constant is 8.617 e to the negative 5. You're right, it was Planck's. Dadgummit. It was a different Russian theoretician. That's KBT. KB times T is the temperature. But Boltzmann constant, when you look it up, it's very constantly not reported in EV. They do the joules. But for what we're doing, yeah, that's not even the right units. You could convert that to the right units. But it's more common what we're doing for Boltzmann constant. We want the one where it's in EV. So yeah, 8.617, just saw it. Right here. This is, I put it on the test anyways. 8.617 e to the negative 5. That's electron volts per Kelvin. That's on the test.
T temperature?
T is temperature. That needs to be in Kelvin because you saw that the Boltzmann constant was in EV per Kelvin. Any other questions about this? That's an activation energy for vacancy formation. We've been talking about lots and lots of activation energies for creep, for diffusion, for all these different things. They all are, it's not like the same thing for all materials. They each are specific to the phenomena we're talking about. Say again. Depends on if I was asking you to tell me the total number of vacancies in that 4-gram lump of material, then yeah, I'd have to give you the vacancy formation energy. Any questions about this? I think it's pretty straightforward.
But we wouldn't have to solve for it separately, right? We would use this equation.
The vacancy at formation energy?
Yeah.
You could. It's on the test. Yeah. The point is that the vacancy formation energy is a constant over some range of temperature. So if I did have you solve it for some low temperature, like for example, if I gave you a plot of, how could we make this look linear, right? NV over N equals exponential of negative QV over KBT, right? We can make that look linear by taking natural log of both sides. So you got natural log of NV over N, right? If we plotted that against 1 over temperature, then the slope will be negative, and the slope of that will be QV over KB. So I could give you that. I could give you a plot like this, and you could figure out, using this plot, what the formation energy is for vacancies. And then you could use that at a different temperature. Like this, if the plot stays linear, then you can use it over that range. That's not on the test. I think I just give it to you, I think I just give you the vacancy formation energy. Okay. Any other questions about this? Feeling good about vacancies? Okay, let's keep moving. All right, Fick's first law, and we're doing it for thermal transport. We also call this Fourier's law, right? So Fick's first law, what sort of scenarios can we use Fick's first law versus second law? What's the difference? Steady state. Does that mean that there's no heat transport? Nope. It means what? It means it's not changing. It's constant with time. It's steady, right? So we're going to write Q, since we're talking about heat. This is the flux of heat. Q, by the way, normally we think of Q as just energy, not as a flux. We usually use the variable J for fluxes, so we have to modify this. But Q is equal to negative kappa dt dx. What's kappa? Kappa's thermal conductivity, not diffusivity. Thermal conductivity, right? Not diffusivity. And if you do the units on this, it doesn't work right now. Like if we look at it, the units don't make sense. Because Q, if it's heat, if that's just the actual amount of heat that's transported, then let's say that's in joules. Well, this is equal to a negative, ignore the negative sign for a minute. That's equal to a watts per meter Kelvin. That's thermal conductivity's units. Multiplied by a delta T, so that's a Kelvin, over a delta X, that's a meter. So multiplying this, the Kelvins cancel, and you end up with watts per meter squared. And that is not equal to joules, right? So a watt is a joule per second. So we could write this is actually a joule per second per area. And that does not equal joule. So this equation works for a flux. And Q is not a flux. So it's much more accurate to write, and the books don't do this, but it should be JQ, right? The flux of heat. Because then you know, oh, J, that means that it's the amount of something, in this case heat, but per area per time. Does that make sense? Is that clear why that is, the unit analysis? Basically, you can't have joules over here or the units don't work. This needs to be joules per area per time. Okay? I feel like I might have just confused people. Yeah? So the left-hand side of the equation, right? Well, how about this? If you want Q on the on the left-hand side of the equation, if you do want Q over here, what do we have to add to this other side of the equation? We have to have, A and T. Yep, that's right. You have to have A and T on the other side. This has to be A, T over there to make that work. Because Q is just energy. It's heat. It's an energy. It's not a flux of heat. The J is the flux. And so they do it right with diffusion. They do it wrong with heat. Well, it's not wrong. It's just confusing. Well, you need an A and T in the denominator when you bring it over there. Am I messing that up?
No, you're correct.
No, that's right.
We just saw it the other way in the homework where it was Q
Yeah,
over AT.
that's right, I think.
equals negative K.
Yeah.
So that's why.
Because think, on the right-hand side of the equation, this is what we have right now. Without that addition, we have joules, but per area per time. So if we multiply this by area and time, then these cancel out, and it's correct. So yeah, that's right. That equation has written up there. Let's circle it. This right here, that is correct. It's not what's in the book, but it's the correct version of this. Well, the more, it's tougher to mess that one up anyways. Okay.
So dx is thickness usually?
That's your thickness. Yeah, it is definitely your thickness.
dt is the difference in temperature.
Difference in temperature, right? So for example, in the, think of the wetsuit problem. You've got like the person, and they are at some toasty temperature, 98.6 or whatever we are. Actually, that's apparently not like human temperature. Sort of like it's not. It's actually off a little bit. I'm pretty sure. I could be fake fanning it here, but I'm pretty sure. No, I think that just like, it's not like all humans have that exact temperature. It's actually off a little bit. In any case, it doesn't matter. You've got cold water out here and you have warm person over here. So if you're solving for flux of heat, the amount of heat that you're losing, then it totally depends on the thickness of this, right? That's why a thick, like a 5 mil wetsuit is much warmer than a 1 mil, right? A little summer wetsuit. Because this thickness is changing. Even if the material is the exact same, they might both be made of polyurethane. They probably are. Neoprene is basically foamed polyurethane. Yeah, Pramit? So if, let's say this is 3 millimeters. So let's assume that we know these temperatures. Let's just call it 98.6 and, I don't know, 10, what do we call it, 40 degrees Fahrenheit, right? You would convert those Fahrenheits to Celsius, right? I'm not going to do that because I don't know how to do that in my head. So we're just going to say DT, right? You could do that. And then DX, the way that they show this in the book is they show this like on a plot. Let me switch colors. Okay? So over here, let's say we're plotting temperature as a function of X. You would see a temperature gradient, and it would be linear across that material if this is Fick's first law, meaning steady state heat flux, right? So if this point up here, if that were to represent 98.6, this one down here would represent 40 degrees. So the way that they end up with the dx is you could assign any distance, like, I don't know if you're starting from the middle of your body or what, doesn't matter. If this is the middle of your body, maybe this is like 10 millimeters here, well, whatever it is, like not more, 10 centimeters, whatever it is, right? At some point, the point though is that from here to here is 3 millimeters. So it's just 3 millimeters that you use there. So it's how you define the problem. Let's assume that we're defining it like this, and I'm just going to put numbers here. Let's assume that this is at like 103 millimeters and this is at 106 millimeters. Okay? So when you do this, dt minus dx, let's call this T person, and this is T water. This is right here X person. This right here is X water. So dt dx would just be equal to T P minus TW over XP minus XW. This is the exact same as if you did it backwards. TW minus TP over XW minus XP. It's no different. Exact same. Yep.
Is area cross-sectional area, or is it surface area?
It's not this cross-section area, it's surface area. Yeah, right? We're looking at a cross-section here, but this would be happening all around your body, right? Everywhere the wetsuit covers is surface area where you're losing heat, so it's the surface area. Now, we often think about these as windows, right? So it's a planar window, but you could do a wrapped curved surface like your body too. Same thing. Any questions on this? And don't forget the negative sign because heat travels down the concentration gradient. That's why we end up with a negative sign here. Question? How do you find the surface area? Well, in what problem?
Like I know there's like a couple on the homework where we had to like
Figure out a surface area? Well, let's say we're doing a heat loss one. Okay, let's say that like we're doing like the wetsuit example here. We say that we're not putting a person in there, but let's say you had like a water balloon filled with warm water, and you put that in the cold water, right? So that way we remove biological processes that produce heat, right? Because our bodies are producing heat. We're heat engines, right? Let's take that out of the equation. You've just got, now it's no longer a person, it's just a balloon. That's body temperature, okay? So you could ask what area would be necessary in order to have this balloon change its temperature by 1 degree after like 1 hour or something. So what you're doing there is you're going from the balloon temperature to a new, sorry, let me rechange that. You're going from the temperature of balloon 1, you're going to temperature at balloon at some other time. How do you do that? How do you go from temperature there to temperature there in terms of heat? You have to use the specific heat. All right, this would be the heat capacity, same thing. You use heat capacity to figure out, that tells you how much energy. So now we know the total amount of Q that must have left the balloon. For it to go down 1 degree, we could use heat capacity of water. If we knew the volume of this thing, we could say, okay, we know how much heat had to be pulled out of it. And then you just plug this into our equation we just did. Negative kappa dt dx at. So if time was given, right, and you knew what the difference in temperature was, and you knew the thermal conductivity of a balloon, you solved for the amount of heat that had to be pulled out of it. The only thing you don't know in that scenario would be the surface area. So yeah, I guess you could answer that question. Yeah.
So that's using the MCAT equation?
What do you mean MCAT again?
Q equals MC W.
Q equals what now? MC what?
MC CB.
So you said use the
Heat capacity.
yeah, to get Q. Is that
So heat capacity, remember, heat capacity is equal to, it's the amount of energy, so it's joules, over some amount of material, either in kilograms or moles, multiplied by how much, the delta T. So if you were to rewrite this, this would be Cp equals Q, that's our heat, over mass delta T. Yeah.
CP is synonymous to specific heat.
That is specific heat measured at constant pressure, which is the most common way to do it. You can also do it at constant volume. I mentioned that in the video. Pressure is the most common one, though. And when you hear people mention specific heat like I did, specific heat is just the heat capacity. Is that the one that's divided by water? It's normalized either by the value for water or by its own mass. I can't remember. It's by mass, isn't it? Yeah. Other questions about this? About Fick's first law? Now, if we go back to that balloon example, like the balloon, I'm asking you, how big does a balloon have to be? Like, what's the surface area for it to go from whatever, some temperature to a new temperature? Is Fick's first law valid? What do you guys think? Is Fick's first law valid for that question? Because the temperature's changing. If the temperature's changing, then the driving force is changing. So technically, the flux wouldn't be constant. So it would be an approximation to use Fick's first law there. But technically, for Fick's first law to be used, dt dx cannot change, right? This has to stay constant, otherwise this is changing over time. If this changes over time, then technically we should be using a different solution, something like Fick's second law. We couldn't use the Fick's second law solution that we showed you because that only works for a really big sample where it stays some temperature far away and you have a different temperature at the surface. We call that the semi-infinite body solution. But when you guys take PDEs, you'll learn all sorts of crazy other solutions of partial differential equations, and this would need its own solution technically. Now, because we're only changing, say, 1 degree, then dt dx doesn't actually change very much, so it's probably okay to use Fick's first law because your error is not going to be big, but there will be an error because the driving force is changing, so you need a different solution. Other questions about this? Right? I see something percolating.
if temperature can't change, why is it DT?
The difference in temperature has to stay constant. So across your membrane, if let's say take like a human being, our bodies regulate our temperature. If we start getting cold, we start burning more fuel and doing things like that. In order to maintain this temperature at 98.6, the water, if it's a giant lake, you're not changing the temperature of it by you being in it, not very much. It's not changing you very much, so this is constant. because it's constant, we can use fixed first law. How about in your home? If you have like a window, you keep it at like whatever temperature you set your thermostat at. You know, whatever degrees you set it at. The outside, at least over some period of time, it's not changing very much. So this is constant. So figuring out the flux of heat traveling through your window, fixed first law is a good thing to use there. But if you're doing this over like day to night, you couldn't use fixed first law because in the nighttime, your outside temperature is very different than your inside temperature. So you can't just say like, oh, over the course of 24 hours, dt dx is the same because this is swinging up and down. And maybe even inside is changing, depending on what your thermostat's set to do. Okay? That's fixed first law. Should we keep going?
Yes.
I feel like we've said stuff enough about that. Okay, next up is Weibull probabilistic analysis. And I say, could you determine failure rates for different materials if their equations were provided? And by equations, these are the Weibull equations. So if I gave you, for example, that the natural log of 1 over 1 minus f equaled, I don't know, say something with a Weibull modulus of 10 times x minus 15. And I gave you another material that was natural log of 1 over 1 minus f is equal to only 5. It has a lower Weibull modulus, x minus 5. You've got two different equations that tell you a lot of information about the probabilistic failure of two different types of materials, red and green here, right? We'll call this B and A, okay? So, for these materials, if you worked at a company that's making both of these materials, could you figure out the failure rates of these two different things? Well, the answer to that question is it depends on the failure condition, right? Which is going to be related to x, right? X is natural log of your failure condition. Let's just do something simple like stress, right? So if this represents natural log of your failure stress, sigma f, okay? And if I gave you a stress, like let's say 100, right? If it's 100 megapascals, assuming that this was with units of megapascals, like the stresses that were used to generate the Weibull data was in megapascals as well, then you don't have to turn this into pascals or anything. You can use it exactly as it is. Then to solve this question, you would just plug in natural log of 100 into each of those for x, right? So you would do, for example, this would be 10 times the natural log of 100 minus 15. Somebody tell me what that is. And then on this other one, it would be 5 times natural log of 100 minus 5. Tell me what those two numbers are.
And the 100 is stress, right?
Yep, that's your stress. That's your failure criterion. That's the thing that's making it fail. That could have been time or elongation or whatever we wanted. In this case, it's stress. That's the most common thing. Pramit?
Yes, so is the units of the sigma
That's a common way to do it. It would depend on the question. So oftentimes when you see this plotted, it might look something like this if it was given in a plot form. And I've given you the equations on the thing, and I've told you what to expect. But if it was given in a plot, then your x-axis might be listed as natural log of, oh gosh, what have I done? What just happened? All right. Oh, I think I hit the down button with my arm. It'll usually put MPA, if they're a responsible scientist, they'll put that in there to tell you that that is given in MPA. A lot of times that's not done. Yep.
So the failure condition is just like once it gets to this point, it's going to fail? Like that's when it starts to deform permanently?
So the question is, if you're the company that makes these two materials, and then I say, we tested a whole bunch of samples, and there was some variability in your data, because there will be. We talk about that variability in data, and we make it probabilistic in our design by doing Weibull analysis. But then when you go to actually use this thing, whoever on your team says, okay, we have to have a stress of 100 megapascals in the real world. This thing is going to, in the real world, when people buy it and use it, it's going to experience 100 megapascals. The question is, what will be your failure rate for those two different materials? That's the question. Okay? So to answer that, yeah, that's like the real world. This is what it's going to see. So the way that you answer that is you plug in 100 for your natural log of your failure criteria, natural log of 100. You get some numbers. What's the first one?
31.05.
What's the second one?
18.025.
So you could then set both of those numbers. You could set them equal to 31.05. You could set that equal to natural log of 1 over 1 minus f, and you could solve for f. Okay? You could do it for both of those and figure out what f is. I'm just going to use a solver because it's faster. Instead of taking the... You could also take e twice and rearrange it. I think this will just be faster. So 31.05 equals natural log of 1 divided by 1 minus f. Add some parentheses. And it is almost 1. This is basically... It's so close to 1, it's approximating it as 1. So me making up numbers was not very effective here because it's basically 100% failure rate. To the accuracy of my calculator that wants to spit out digits, it's like it always fails. Let's try the other one, 18.02. $18.025, same. Yeah, it's basically going all the way to 1. So that won't happen on the test. I'll give you things that I've actually run through Excel and made sure that they actually work. But that's how you do it. You would solve for f. Let's assume that f equaled a value like, you punched it in and it was 8.66, 0.866. That's your failure rate at the given stress, right? So then if I said, okay, you make 1 million parts, how many can you expect to come back as failures that customers are going to return? So you say, okay, out of 1 e to the 6 parts, what failure rate can you expect? Well, failure is equal to the rank of failure, right? The order in which it failed minus 1/2 over your total number, which is 1 e to the 6th. Okay? So, so you could plug in this for f, and you can figure out the order in which it failed, right? Is it the 20th? Then you have 20 parts fail. Is it something higher? Like, let's plug this one and see. Where the number is what we're solving for. This is the number this is the total number that are going to fail out of the 1 million.
What is the part after the hashtag?
Minus 1/2? Oh yeah, that's just how we calculated f. That's something we did in class. To determine f, you do the rank in which it fails minus 1/2. The reason why they do minus 1/2, let me just briefly show you this. It's because if you don't have that, you get problems. Let's say you tested, let's say that you tested like 5 samples, right? Sample 1, 2, 3, 4, and 5. And this one failed at 10 MPa, 11, 12, this was like 13 and 15, okay? So if you calculate your failure rate, then you do the number which it fails, the rank, right? Remember, this is equal to, you could just do like 1 over the total number, right? And you would say that this one has a failure rate of 1 out of 5. That would be one way to do it. And this would be 0, it'd be 20% failure rate. Or in other words, if you take all your samples up to 10 MPa, 20% will fail. And if you take it up to 15, then you get 5 out of 5, and you're going to get 100% failure rate. So that's not very good because that's assuming that literally if you were to test now 1 million samples, you're always going to get 100% failure rate there. But that doesn't make sense because we know that if we went from 5 samples and we actually tested 1 million, the odds are of something going above 15 megapascals is higher. So we can't believe that that's actually 100%. So the way that they fix that is by doing this modifier. That's not erasing. Be cool, EndNote. All right, what's going on with EndNote? But you basically, instead you say the rank, the number minus 1/2 over the total number. So that's going to be equal to 1 minus 1/2 over 5. So that's now equal to 0.5 over 5. So in other words, it has some survival rate. Because again, if we went from 5 to 1 million samples, something's going to break it lower than 10. So we give it some survival rate. Does that make sense?
Yeah, I forgot about that equation.
Okay. Midterm review. So yeah, you could figure out how many parts you expect to break out of that 1 million by plugging it in there. In this case, it's pretty bad. It's going to be a lot of parts are coming back. That's probably not a very good. If a large number are coming back, that's maybe something that's a problem. You either need to change its use condition, like that car can't go over a certain speed that would produce that stress, or whatever it may be. But otherwise, you're going to get too many failures. Otherwise, you got to move to a stronger material. Yeah, Eric.
So that minus 1/2 is fairly arbitrary, though. It's just
Totally.
deciding that number.
And there's other ways of doing it. Like if you look up, there's other ways of doing it. There's one where it's like minus 0.3 divided by something plus 1/2. It just gives you, more realistic failure rates. So let me see if I can find it. There's other ways to do it though. I can find it for you offline. There's other ways to determine failure rate. This is just a quick and easy one, and it works pretty well. Yeah, Ryan?
What's the equation that has Weibull modulus in it?
The raw equation looks like this. The raw equation looks like that right there. So your failure rate is equal to 1 minus the exponential of whatever the parameter, the point at which it failed, divided by a constant, sigma naught, which you determine for your system. That's called the scaling parameter. And then that whole thing is raised to the m, your Weibull modulus. And because that's not linear, and it's easier to work with linear systems, we do a little bit of algebra and make it look linear by plotting natural log of f, sigma f, and natural log of 1 over 1 minus f.
Oh, so that's just the alternative to the natural log.
It's the exact same math. We just linearize it, which makes it easier to get the Weibull modulus from it. This was because back in the day, they didn't have calculators that could do nonlinear regressions very easily. Nowadays, it's trivial. We don't have to nonlinearize it. You can just plug it into Python, give it the actual equation, and have it fit m and sigma naught if you want. That's no problem. It'll give you the exact same math.
On the test, we should use the natural log.
On the test, you won't have to do that. I'm giving you the Weibull modulus. I give you 2 equations. I literally give you these equations, and you just use them. Because we don't have a lot of time. Okay? Any questions on this? That straightforward? You can figure out failure rates? Let's keep going. This is one I think we need to spend some time on. I don't think we spent enough in the video on this. So it has to do with thermal stresses. Thermal stresses come about because materials expand at different rates, right? Because they expand at different rates, you end up with this scenario. You've got material, we'll call it X, and it's bonded to material Y. Okay? Those two things are bonded together. What happens when you heat them up? If this is at room temperature, you superglued those two things together, or welded them, or whatever you did to it, clamped them, you put those two things together. As you heat it up, these things have different properties, right? So you could say that the thermal expansion, alpha Y, if it's a polymer, what's a typical ballpark value for thermal expansion of polymers? And if X is a ceramic or a metal, let's do a metal. So metals are something like 50 ppm per K in that ballpark, 10 to 100 range. Let's call it 50. That's actually kind of high, but we'll use it. So it's 50 ppm per K, whereas a polymer is typically over 100. Let's call it 150. ppm just means that you could actually write this 150 e to the negative 6th per K. That those are equivalent. Just means parts per million. You've just divided it by a million. This thing would be 50 e to the negative 6th per K. Those are equivalent. Okay? So those things are going to expand at different rates. If you heat this thing up, which one's going to expand more? The polymer would love to expand a bunch more. It would like to maybe go that high, whereas the ceramic or the metal, whichever this is only going to expand a little bit. Well, that's what it would like to expand. But they can't expand different amounts because somebody bonded these things. You put an epoxy or you welded it or you did whatever you did to it. So now what they have to do is instead of doing their own thing, they have to meet in the middle and they have to have some net overall expansion, right? Okay? And because of that, the yellow, the Y material is going to be compressed, right, from what it wants to be. It's feeling actually squished. And X is being put under tension, right? You guys follow me? So you've got, that's the first step, is to figure out which one's under tension and which one's under compression. This one's going to be under compression. This one here will be under tension. Okay? So then you could figure out the actual stress. We haven't yet turned these into a stress yet. How do you turn it into a stress?
Use Young's modulus and then the strain.
Yeah. So the strain would be given. Let's say that you know how much it goes, right? Or actually, we could use this expression. The thermal stress is going to be equal to Young's modulus multiplied by delta T, how much you heat this thing up or cool it down, multiplied by the difference in thermal expansion, right? So in other words, we could rewrite this, your Young's modulus, and this has to, and you'll notice Young's modulus, we have two different materials. This means that this thermal stress, you don't get one thermal stress. Each material gets its own thermal stress. So what we really need to write is thermal stress for X, then you're going to use the modulus for X. Whereas if you wanted the thermal stress for Y, then you use the modulus for Y. Okay? Does this make sense? It would be given in the problem, yeah. So let's say we're doing it for X for a minute. Okay? So that's going to be temperature final minus temperature initial. Final minus initial temperature. And then it's going to be your thermal expansion difference. So it's going to be the coefficient of thermal expansion of, let's just do the larger minus the smaller, y minus x. Okay? If you switch it, it will change the sign of your stress. But what we know is that the stress is under tension, so it doesn't matter. Whatever comes out, you know, make it, doesn't matter if it's positive or negative, you know that's the stress under tension. Right? Everybody clear with me so far on this? Straightforward. So you could actually then say, let's say this generates 100 megapascals of tension, but your material yields or fractures under 70 megapascals. So that would tell you that X is going to break under this scenario. You heat it up and X is actually going to fracture to accommodate that thermal stress that it's building up in it. And this, by the way, this is super, super, super common. We as engineers underestimate the role of temperature fluctuation because we bond things together. We make big old bridges and buildings and devices and we weld them and put them together. And then they expand at different rates and it builds huge stresses up, especially if you're putting together materials that have very different thermal expansions, which we do all the time because you want to put glass in buildings. And glass, right, expands not at all. And your building might expand a fair bit. So if you don't have something that can mediate that mismatch of stress, like the sealant that they put around windows, your windows would be fracturing for sure, right? Yeah, Landon?
Would the same problem occur with like alloys, where like you're melting things together, so now it's like a new compound?
No. If it's a single phase, then overall the alloy expands at a single expansion rate. Now, what you're saying is like, well, the individual elements that went into it, as pure metals, those expand at different rates. Once you melt it and it becomes a single phase, it has one set of properties. Okay. Yeah. Ryan?
Compression is negative, correct?
It depends on how you define it. In this class, I've been defining it as positive. Yeah. But it doesn't matter. The number that you spit out, you know that because you did this analysis up front, it's under tension. You know, the sign doesn't matter here.
And you were able to tell which one would break by just comparing the stresses?
Well, I'd have to give you the yield strength or the ultimate tensile strength or the fracture strength. I'd have to give you some of that information, and then you could tell me, like maybe it's not even going to break, but one's going to be permanently deformed, right? It will yield. Like let's say that the polymer gets stretched. It might be permanently stretched. So then when you cool it back down, now it's permanently stretched and it's going to try and shrink. That might lead to buckling, right? And you get polymer buckling of films. Yep.
Is Young's modulus the same thing as elastic modulus?
Yep. We've been using those interchangeably. They're the same thing. Stiffness, Young's modulus, elastic modulus, those are all the same thing.
And then would you expect us to calculate Young's modulus?
I could say in this problem, I don't remember what I actually gave you. I think I actually give it to you. I'm pretty sure I give it to you. But I could give you stuff to calculate. I could say, before you bonded these things, when you applied such and such a stress to material X, you observe such and such a strain. And from that, you could do Hooke's law, sigma equals epsilon E, and you could solve for E, Young's modulus. In this problem, I just give it to you, though. But that's just Hooke's law if you wanted to solve it from other data. Hooke's law, if we go back to chapter 7, this is like your mechanical engineer's jam. You guys love this stuff. Hooke's law is just right here. Stress is equal to the elastic modulus times strain. It's the constant of proportionality that tells you how much strain you get when you apply some given stress. So yeah, and you could solve that if I gave you a curve like this, but with numbers on it. This one has numbers actually, right? You could tell me what the modulus is. For this material, it's going to be the slope, right? It's the constant proportionality. So you could say, okay, it reaches 0.01 stress, whatever the units are of this, and here's a strain is 0.01. So you could figure out the slope of this. That would be your elastic modulus. That's not on the test. I just give it to you. Jared? That's you. I just give it to you on the test. But that's a really easy question that you should know how to do. If it's not constant, we don't do that in this class. We do linear elastic, not nonlinear elastic in this class. Figuring out the elastic modulus, if I gave you this data, it would be a cinch. E here, that's your elastic modulus. You just take that by taking the slope of the linear region before it starts to permanently deform. So you would read values off of this plot, and you'd take the slope. You'd do 2 points, take the slope. Pramit? Is the relaxation modulus on the test? I don't think so. Nope, not on this test. No relaxation modulus. Might be on the final. It's a favorite. Too painful. Too soon. So are there questions about thermal stresses? Does this approach make sense? Could you do it in reverse? If you bonded it at high temperature by melting a glass, this is how you bond ceramics typically. 2 different ceramics, it's very common. You put some glass frit along the surface. You heat the thing up so the glass melts. So it's in a molten state, but as you start to cool it down, that glass solidifies. So you've bonded your material. Then as it cools down, think of this in reverse. Hint for the exam, right? Okay, Fick's second law for mass transport. Okay, so mass transport means we're not doing heat diffusion, we're doing mass diffusion. Okay? The equation for Fick's second law for mass transport is as follows. The composition at some point x is going to be found by knowing the composition deep within the material, C naught, knowing the composition at the surface, setting this equal to 1 minus the error function of x, your position where you want to know the concentration at, divided by 2 square root of dt, where d is your diffusion coefficient. This is the same guy that we used in chapter 6, in the first part of chapter 6, which is d equals d naught times the exponential of some activation energy for diffusion, QD, over kBT. Okay? Yep.
So when do you use the KB or the R?
Yeah, we mentioned that a little bit earlier. If you're talking about something that's happening on a per atom basis or a few atoms, it makes more sense to do KB because it's been divided by Avogadro's number. KB and R are the same thing, except that R, if you divide it by Avogadro's number, you get KB. So if you're doing something on a per mole of substance, like we did with free energies, we were talking about what's the change in free energy when you transform a mole of, this compound to this compound. It doesn't make sense to do that on a per atom basis because you could be talking about billions and billions of atoms. But if you're talking about things that happen on a near atom basis, like an individual atom hopping through the lattice, that makes sense to do with KBT as opposed to R. Yeah. Yeah, I will give you an error function table, so you don't need to take up note sheet space for that. Good question. That's on there, but you do need to know how to do linear interpolation on it. Remember what that is? Or Ryan, other question?
Yeah, what are the C's again?
C's, those would be your concentrations. Because why are we using concentration here instead of temperature for mass diffusion? What drives mass diffusion? What's the driving force? It's dC dx. The difference in composition, the composition gradient, is the driving force for mass diffusion. For heat, it was a difference in temperature. Your home is warm, the outside's cold, heat moves outside of it. You're going to use it. So you need to know how to use that equation.
How would we use that equation?
Can you do an example?
So let's say that you were given D, or you interpreted D based off of things related to polymers, and then I said, what temperature is it at? Or what was the formation energy or whatever, right? It's like anything. I give you everything but one variable, you solve for the other thing. Pretty straightforward. Yeah.
Besides looking off a graph, how do we find D0?
One more question.
Besides looking off a graph, how do we find D0?
Oh, besides looking off a graph, how would you solve D0 if I didn't give you a graph to solve it graphically? I could say 2 different temperatures, and you could solve 2 equations, right? If I gave you 2 points, 2 different temperatures, right? Because the assumption with this is that this is a constant, and this is a constant. So we have 2 unknowns that you could solve for. So if I told you the diffusion at this temperature, say 500 Kelvin, and then I said you could also solve, you measure the diffusion at some other temperature as some number at 700 Kelvin, you have 2 equations and 2 unknowns. So you could solve it that way. You could divide the 2, the D naughts will cancel, and you could solve for activation energy. And then you take that activation energy, the temperature, and plug it back to that. I don't think I have you do that on this test, though, but you could do it. I think that's it, gang. I think we finished early. Other questions? Yeah. Yeah, so let's do that. So if you had this is your equation, D equals D naught exponential of negative QD over KBT, right? That's our equation. If it's on a graph, it's very often going to be, let's just look at one. Something like, okay, like this. So this is a really common graph. For these. So we could use this to figure out our diffusion coefficient constants, right? So we could do it a couple ways. We could do it the way that I just described to, remember your name again? Seth. And the way that we do that is we just pick 2 points, 2 equations, 2 unknowns. You'd say, great, it intersects this point right there, this point right there. Because this is a log plot on the y-axis, make it easy on your life and pick things that intersect these really easily, right? So you'd say that this point right here is, call it 0.94, 0.94 and 10 to the negative 14th, okay? This one up here is right in the middle by my looks, so 0.85 and 10 to the negative 13th. So you could do 2 equations, 2 unknowns, and solve that if you wanted. That would be one way to do it. Another way to do it is to recognize, oh, well, the only reason that's linear is because this is plotted in a log axis, right? They've made this logarithmic scaling here, and they've plotted this as reciprocal temperature, 1 over temperature, right? That over there is 1 over temperature, and they've actually taken and it's actually divided by 1,000 to make these numbers not big numbers, okay? So to do that, you could take the slope between those and figure out the activation energy from that. Just doing the 2 equations, 2 unknowns is as easy as anything, I think.
And what are the equations that you would use in that case?
This equation right here, you would write it 2 times. The first time you would plug in what? You have 2 different temperatures, right? Your x-axis is reciprocal temperature, so you'd have to turn that into a real temperature. If you're going to use that equation, that uses real temperature, T, but this is plotting 1,000 over T. Is that right?
So you have to do 1,000 divided by your 0.94.
I think it's actually T divided by, this is temperature divided by 1,000, right? If your temperature's at 1,000 degrees, then it would be,
Per Kelvin, so 1 over Kelvin.
this one.
Because I think it would be 1 over T, so it would be a fraction.
It's definitely 1 over T. And this is definitely hot and this is definitely cold.
So you would multiply it by 1,000.
In any case, you'd have to convert that x-axis to a temperature in Kelvin. Then you plug it into this equation right there for temperature, right? And the y-axis you read right off of there, right? This 10 to the minus 13th, you plug that in for this d. So then the only thing you don't know is d naught and qd, meaning if you have two of these equations that are different, you could solve for them. However you want to do it. Yep? So the slope is the qd? The slope is not qd. It's qd over kb. Right? Because they did not include the Boltzmann constant here. So it's actually, this slope is qd over kb. It's technically the negative qb over kd. Because you're going to get a negative slope, but activation energies aren't negative. Yeah.
So if we were doing a graph on the test, would it look similar to this, like diffusion coefficient on the left, temperature on the...
On the x-axis? Yeah. That's right. I think the one on the test is different, but I'm not asking you to solve for the diffusion coefficients, so you don't need to. Other questions? Yep.
Could you explain more what you meant about doing it in reverse when throwing the stress? Like, would we still be solving for the stress?
So let's assume that you're still solving for stress, but in this scenario, you bonded it at room temperature, you put super glue on there, and then you heated it up. Just think what it would do if that was reversed. If it was instead bonded at high temperatures, so now it's stuck together because you put glass that melted or something, and now upon cooling, you just have to think of it in reverse. Yep. Your delta T is negative, but if I were you, I would draw the cartoon, before versus after. The one that expands more upon heating will shrink more upon cooling. I would draw that. Yep.
I just want to make sure I have all the equations that I need. Maybe you can quickly go through each Boltzmann and say the affiliated.
It's all there. Yep, that's it. Okay, good luck, everybody.